Okay, have you sent the materials yet? Okay. Nah. Okay. Well, I have some of the papers back here. So we how many papers have we gone through together? If I'm not mistaken, we've
We've
gone
done
like
like one.
one, and then we didn't start the others yet, right?
We did like a part of it because you didn't take radiation.
Yeah. But basically, we finished only one, right? One paper.
Yeah, we can do
Okay.
another one now if you like.
Right. Because I'm just looking here. I have the 2018 paper. Let's see which one haven't done yet. Okay.
So have we done any of those subjects that are in the list?
I
We have done.
Yeah, we did. We have actually. All these topics are everything except radiation, radioactivity. Yeah.
So we've done all of them.
Yeah. Okay, so let's
Perfect.
let's go through the past papers then. Hold on, let me just fix my board here. Ah, that's not working. Okay. Why isn't that working? Why my Jamboard's not coming up? Hold on. Okay, we'll just do that. I have an idea. Okay. And
I think we've
here
done this.
we go.
We've done this paper.
Yeah, we've done that one, right?
Yeah.
Okay. Let me just check. We've done this problem before, right? Hold on, it's pasting. But is it showing properly now? Okay. Have we done this problem yet?
Yep.
Yeah, we have, right? So we skip that. How about this problem?
Yeah, we also done that. We did it like it's on the bottom right and left.
Okay. So, wait, am I sharing my window or just a tab? Let me see. Oh, you're seeing my camera. Okay, never mind. Yeah. So we've done this. How about this one?
We've done the whole thing.
This is radioactivity, so we'll keep that away for now. That's also radioactivity. Here. Have we done this one?
We've done every single question.
Yeah, we've
other
done
than
all of
the
these. All right.
physics.
So what that was. Okay, we've done
We
all
just
of
do, like, a
that.
different
This
paper
is the
or-
higher tier. This paper 1, foundation. We've also done this one, right?
I believe so.
I believe so too. Yeah, we've done this one. So let's do this. Oh no, sorry. That's the mark scheme. Here. Oh, sorry, that wasn't the marking scheme. That was the data form. Yeah, equation sheet. Okay.
That's the equation.
All right. How about this one?
Isn't that common knowledge, right?
Yeah, of course. But let's just make sure that this is correct, right?
Uh-huh.
So,
Milky Way.
Milky Way, right? Okay. How about this one? Like, okay.
So I can see you're sharing your board.
Oh,
You're
I better
not
stop sharing then. All right. Okay. How about this? Well, this is foundation, so the formula is given to you, right?
Yep.
Okay.
Oh, this is foundation.
Yeah. I think it's still worth.
Foundation paper at once.
Yeah. I haven't downloaded any other papers yet. All I've down. Well, I have one more paper here. Maybe this is the higher paper.
Yeah, higher.
Let's go to the higher tier then. Yeah. Okay, so let's go to this. All right. I think this is worth our time now. Okay. So we have this. You have a child dropping a ball. The ball hits the ground and bounces. Figure 1 shows the velocity time graph for the ball from when the ball is dropped until when the ball reaches the top of its first bounce. A resistance can be ignored. Describe the motion of the ball between points A and B. So what's happening here?
I'm trying to solve the question. Describe the motion of the ball between points A and B. So the velocity stops as soon as the ball I think it bounces. Wait. He bounces it when the ball makes contact with the ground at B.
Okay. So what's happening between those points? Is it moving at a constant speed?
It's moving in the air.
It's moving up or down?
Moving at a constant speed.
Okay.
It's moving constant as in like constant as in it's not the same, but it's moving at an accelerated rate.
Okay. All right. There's a better answer for this. Okay. First of all, you said it correctly. You start off from 0, then you end up at it bounces off the floor. It starts the bouncing process here at B, right? What's happening here is it's falling, correct, right? Now, look at this. This is a velocity time graph. Right. So I'll put this in the Jamboard just so we're clear. I'll just put this here so it's easier for us to go through. Okay. When you have a velocity time graph, you can take two things from the graph. So the first one is the gradient or the slope, right? Slope. And what does that equal to? That's equal to the acceleration.
It's moving. Can I just say it's moving
at
a steady acceleration?
Yes, exactly. Acceleration of the object.
And the speed increasing at a constant rate.
Yes. So that's the best way to say it in this case, yeah? So here, A to B. A to B. The object accelerates has a constant acceleration. Okay. Object has a constant acceleration. Okay. And then what else is the other one? The area would be equal to distance covered, right? By motion. Okay, by the object. So in this case, what does this mean? As you go from A to B, that area covered increases, right? Okay, so what's the second part here? The distance traveled, the object travels.
Can I just fix something with my internet?
Okay, go.
Keep losing connection.
Okay. Travels further. Close this, close this. All right, let's take a look here at the second question. What direction is the ball moving between C and D?
Upwards.
Upwards is correct. Okay. All right, let's take a look here. The ball and the earth form a system. What is meant by a system?
System. It's a group.
Mm-hmm.
A group of object that interacts.
Correct. Okay. Right. Number 4. When the ball hits the ground, energy is transferred from the ball to the earth. Explain how the data in figure 1 shows this energy transfer. So going back to the graph, how do we know that energy transferred?
Wait, what was the question again?
From B to C, okay.
Yep.
When the ball hits the ground, energy is transferred from the ball to the earth. Explain that, how the data shows the energy transfer here in the graph. Okay, I'll give you a quick hint.
At the top of the bounce
Uh-huh.
is less than the height when it was dropped, right?
Uh-huh. How do you know that?
Because it appears to be from 0 to 7,
Mm-hmm.
and it shows -5 to 0. So
Okay.
it's less.
All right. So there are two ways to answer this. One is with speeds and one is with distances, right? Okay. If you do speeds, then what do? You compare the speed at B to the speed at C. So you did it correctly, right? If you're going to do distances though, what are you going to compare?
You're going to compare the... Wait.
Okay, let's go back to this idea.
You can calculate the length of AB.
Okay.
And compare it to CD.
Okay. Here's another way you can compare it. Remember that, okay, one way you can do this, I'll do this here on the Jamboard here. The first way is compare the kinetic energy before and after collision, right? After the bounce.
Yeah.
Which means compare speeds, right? Okay. The second way to do it is to compare GPE, the gravitational potential energy. And how do you do that? You compare heights. How do you compare height? Look at the areas, graph areas. Because remember,
I had a question
yeah, go ahead.
about, you see how it gives you like the actual graph, like it's from 0 to 0.7,
Mm-hmm.
and from 0 to 6, no, 0 to like 7.
Uh-huh.
Can't you do like Pythagoras to find out the length and just compare it?
You can, but remember that the length of that line doesn't really mean anything in physics.
Okay.
Okay. It can mean something in the geometry of the problem, but it's gonna be much easier to, well, if you're gonna measure this length anyway to use when you want to use Pythagorean theorem, right? But you might as well just find the area using those heights. Okay. So so this is for the last question here. Okay. So what do you look at? What are the so how do you get your 4 marks? Okay.
You get, but you have to say those points, yeah.
Uh-huh. So but I would prefer the kinetic energy comparisons here. Okay. And you did say that, so I think what are gonna be the 4 marks? The first one is speed, not velocity. Yeah, speed at B is larger. As you said this, I'll just note this down. Than speed at C, right?
Should I say my definition?
Okay. Go ahead.
It's the height at the top of the bounce is less than the height from which it was dropped from.
Oh, okay. And then?
So
Okay.
the ball lost energy.
Okay, exactly. So that's the last part. The ball lost energy. Okay.
Yeah.
Okay. 3 and then 4. Okay. So I would say it this way just so we're clear, but yours is acceptable. Okay. So speed of B is so KE at B is smaller as larger. Right? And then what's gonna be the third mark? KE at B, so KE is lost. And therefore transfer energy, lost energy goes to the earth. Okay. So similarly for this part, if you want to compare GPEs, so what you can say here is area AB is larger than area CD. Okay, and then therefore GPE for AB is larger. GPE for AB is larger, so GPE is lost. Like that. Okay.
Okay.
All right. Let's move on. Okay. How about this? Number 2. So you have an investigation to determine the spring constant, and then you have these values. Okay. Now describe a method the student could have used to obtain the data. Oh, 6 marks. This is a lot. Okay. Okay, take your time on this one. This is a lot.
Yeah. Could you like scroll it up so I can see the?
There we go.
Yeah.
Okay, Adam, I'll be right back while you solve this. I'll just take a quick trip to the bathroom. All right. Be right back. Oops, I shouldn't change it. Okay. All right, I'll see you in a while. There we go. I'm just taking a quick bathroom break. You miss me? In the weeks. All right, I'm back. You have your answers yet?
I think I'm like halfway through it.
Okay.
Okay, I got an answer.
Okay. You want to go ahead and walk me through your answer?
So first you set up the clamp stand of the clamp,
Mm-hmm. Okay.
and then you hang the spring from the clamp.
Uh-huh.
I know this because I did this experiment before
Okay, good.
class. Um, you put a meter ruler alongside the spring
Okay.
to measure the centimeters,
Uh-huh.
or like a half meter because you can't go a full meter. Like
Okay.
you use the half meter ruler to record the readings
Mm-hmm.
at the level of the bottom of the spring.
Okay. Good.
You put a two Newton weights on the bottom of the spring.
Mm-hmm.
And then you record the new position of the spring. And then not exactly to like you do that and add weight every single time.
Okay.
You measure the reading of the bottom of the spring every time you add the new Newton, two
Okay.
Newtons of weight.
Okay.
And then at the end of measuring all of it, you measure its extension.
Okay. How do you measure the extension?
You add further weight.
Yeah, that's how you make it
or you use
extend,
the
right?
meter stick to-
Yeah, but what I
Yeah.
mean is, what you did was you found the original length, right?
Oh yeah, you find there's a length that you subtracted by the extension length.
Okay. And that's going to be the actual extension. All right, good. So I'm giving you 5 at the moment because you didn't answer this yet. Your answer should include any cause of inaccuracy. All right, I'll give you the time. Don't worry. Yeah, just add that. Then you tell me, and then I'll tell you if you get that extra mark.
Not keeping the ruler in like a straight position.
Okay. There's a lot of possible. Yeah, there's a lot of possible answers to this. Okay, that's a valid one. The one you just said. I think that's valid. Okay. Here's another possible answer. Your spring, no matter what you do, is gonna swing a bit. It's gonna make measuring the actual length hard, right? Okay, that's another possibility.
But you can't like really change that. That's an uncontrollable
Uh-huh.
inaccuracy.
Yeah, but it doesn't say whether the inaccuracy can be controlled or not, so that should be fine. Right? Okay.
So you should keep the ruler at like the same place. You shouldn't move it.
Yes. Yes, that's another one. Okay, of course, 6 marks. Okay. Oh, okay, the next one. The student measured the extension for 5 different forces rather than just measuring the extension for one force. Suggest why.
To identify any anomalous results.
That would actually be the answer if the question was about the trials. So for each force, he took several trials. Okay. All right. But the idea, yeah, it's not. This is not about having multiple trials, but this is about having 5 data points, 5 different forces.
No, I mean from like different forces. Is it like, are there any like one, for example, extra 2 newtons would be
Actually,
longer extended just because of what the spring was made of?
Okay. Well, that's one possibility, but the best answer here would be it's to ensure that the relationship you get is in fact correct. Yeah.
To reduce the effect of the random error.
I wouldn't say that. It's more for how to say this in a more technical manner. It's so that when you get your graph, you can see whether it's linear or not. And if it's linear, then we can get a relationship. Or at least if it's mathematically possible to linearize the graph. Okay?
Yeah.
All right. In a more technical manner though, this would be the best answer here would be this is to ensure that the graph or that the data has a high correlation. That's the shortest way to say it in technical words. Okay? It's to ensure that the data obtained has high correlation between force and extension. Okay, so after I type this in, let's move on. Yeah, to ensure a high correlation between the values, between the data, among the data. Okay, so let's move on. Next question. So here's the data that we presented, and you put it in the graph, right?
Yep.
Complete figure 2 by plotting the missing data from table 1. Table 1 is repeated here. So what's the missing information?
I know it's plotted exactly.
Alright. I guess we'll skip this because I think you know how to do this, yeah? Okay, write down the equation that links... Yeah, it's 2 marks. I think it's 1 mark per point because there are 2 missing points. Okay. Alright, how about this one? Write down the equation that links extension force and the spring constant.
Force equals spring constant times extension.
Correct. Okay. Hence, with that formula, calculate the spring constant of this spring.
So after rearranging, it would be force divided by its extension.
Yeah, right?
And the extension is 0.2. So it would be 10 over 0.2.
Okay.
Which is 50.
Correct. Okay, but it's 4 marks, right?
Yeah, but if you rearrange it, it would have given the... If I wrote the would have done
yeah, that would be good. Now, another way you can solve this, especially given data, right? Okay, I think in this particular case, if you can use the equation straight away, that's normally like 2 marks, 3 maximum. Okay, 4 mark questions are usually something else. So I would, because it's 4 marks, I would be scared personally to just calculate that. Okay, so what I would do is I'm going to, okay, so while that's loading, I'll copy this again. So how would you do this? You have, well, you're gonna start off with what you said. The force is equal to uh,
Spring constant
a spring
times
constant
extension.
times extension, right? So F is equal to spring constant K times the extension, right? Uh, okay, I'll write that as the word extension. Okay. Now this tells me here that F is on the x-axis. So this is the x value, right? And then this extension is our y value. So this is our slope or the gradient, right? Oh no, sorry, not quite yet, because we wanna that's some value k first, yeah. Now we wanna isolate y on its other side, so we want y equals mx plus b, right? Plus some constant, the y-intercept. Now you can already say that that's 0 because of this, right? Okay. Now what would you do? You need to find this slope, and this slope, if you rearrange this becomes extension equals 1 over k times the force, right? So this tells me that 1 over k is equal to the slope, is equal to m slope. Okay. So yes, I know this is more complicated and you'd rather do it the other way, right? But this is just in case this is what it's looking for, what they're looking for. Okay. So in this case, I just find that slope. I can find that slope. The slope, that would be 20 minus 0 over 10 minus 0, right? That's still gonna give you 2. Sorry, let's not use 20. Let's use 0.2. Right? Because it's in newtons per meter, so we have to 0.2. So that's gonna be 0.02, right?
Yeah.
Okay, 0.02 here. So what do we get here? 1 over k is equal to 0.2, and then k will now be equal to 1 over 0.2, which is the exact same number you got earlier. Wait, am I right? Oh, I'm missing a 0. 0.02 right there. So this still gives us 50 Newton meters. Okay. So again, the solution's the same, but I'm afraid because of the 4 marks, this may be the solution they want. Okay. All right. Just being safe. All right. Let's move on. Okay. Hooke's law states this. Explain how the data supports the student's conclusion. That okay. There.
The line is straight and passes through the origin.
That's the first part, correct. Actually, those are the two parts. Those are the two parts. Curve. Yeah, the line doesn't curve. It's the second part. So, but you said straight, so we're good with that, right? Okay, so it's a straight line, and it goes to the origin. Okay, good. Let's go to this next one. Earthquake waves. Which one is correct?
P waves are longitudinal and S waves are transverse.
Correct.
Bottom.
So this one is correct, right? This one.
Yep.
Okay, next, seismometers record the vibrations caused by seismic waves. Here's a P wave. What is the frequency of this P wave?
Uh, 0.4.
Okay, how'd you do that?
It's 10 divided by
That's correct, by the way, yeah? But just tell me how you did it.
Yeah, 0.4.
Uh-huh. Okay, explain. 10 seconds. How many?
There's point.
Four four waveforms
Yeah, 4 ways.
in 10 seconds. Correct. Write down the equation. Okay, let's go to the next one. Write down that equation. Frequency, wavelength, and wave speed.
Wave speed equals frequency times wavelength.
Correct. Okay. Alright, this next one. The P wave shown above. So this one takes 10 seconds. It travels 7,200 meters per second. Calculate the wavelength.
So 7,200 equals to 0.4 times wavelength.
Mm-hmm.
So that would mean wavelength is equal to 7,200 divided by 0.4.
Okay.
Which would mean wavelength is 18,000 meters.
Okay, correct. Does that make sense for an earthquake? Yes, it does. Okay. Earthquake waves, whether P or S, are usually long wavelengths. Okay. Okay, this one is not really physics as it is, but this is still part of your syllabus. So how does this do that? What? Have you studied this? I think you have, but let's see if you recall.
I know it doesn't travel in liquid.
Okay.
And it doesn't travel on the outer core as well.
Okay.
Right? That's
Actually, they do. They do. Okay. They can travel through the mantle. They can travel through both layers of the core.
outer core. I mean.
Yeah, both the inner and outer core. The earthquake waves, the seismic waves can travel through both layers, both the inner and outer core. Okay.
Wait, can I switch it up just to check?
All right, sure, go ahead. This one's a bit tricky to remember, just so you know.
Yeah, it's because I'm studying for the box like last night, so I'm going through all the subjects.
Right. Okay, while you're looking at it, I'm just gonna see what's the next question. Okay, the next question is no longer waves. The next question is about electricity.
So those P waves can travel through the outer core and through the liquid, not seismic.
Yeah, but P waves are S and P, right? So when we say the word seismic, it refers to both S waves and P waves. Okay, because of this statement again, right?
Seismic just was like S seismic, that's right.
Ah, okay.
Are two types of seismic, okay.
Actually, the P stands for primary, the S stands for secondary.
My bad, I literally
Okay, so going back.
I forgot what it was.
All right, so going back. So, what about this? Well, what you said is actually part of the answer.
So I know they go through the liquid,
Uh-huh.
and since they're both same, they will go through the outer core as well.
Right. Okay. So how would you get your... How many marks is this? 2 marks. Okay. Okay, how would you get your 2 marks here? Remember that, okay, I think I'll post a picture. I'm looking at it right now. Okay, let's go here. Okay. Okay, so the idea is, you're right. P waves can. Which one are the compression waves? P waves. P waves can travel, but there's and S waves cannot, right? But here, the idea here is that because P waves can basically travel through most of the Earth, but they cannot penetrate some parts, the shadow zones are different than the S wave shadow zones, right? Okay. There's a okay. Okay, you see here that P waves can travel through the outer core, but only at certain angles, right?
Yeah.
Okay, so the P waves, when they travel through the outer core, the main reason here that we have a solid inner core here is because otherwise these waves would not look like this. The shadow zone would be a bit smaller, like that. Okay, the shadow zones will be a bit smaller. But for S waves, because the shadow zone is so big, the reason is because they cannot penetrate through the outer core, which is liquid. So you were right when you stated that. Okay, you just had to add a little bit more detail probably on how the shadow zones are formed. Okay. All right, but other than that, you should be fine. Okay. Next question. This is still question 3. Okay. So this is a simple seismometer made by a student. I think, yeah, that kind of works. Okay. Why does the movement of the bar magnet induce a potential difference across the coil? It's just 1 mark, so I guess you only need to say the principle behind it.
The magnetic field, the polar changes.
Because of the yeah, that's right. So when the bar magnet moves, the magnetic field inside the coil changes, and therefore inducing a potential difference. Correct. Why is this alternating? Why does it travel from? Yeah. Why is it alternating?
Because the magnet changes direction.
Okay, the movement of the magnet changes direction. It keeps changing, so the EMF also keeps changing direction or alternating. Correct. Okay. Here, how the potential difference after the bar magnet has been released. Which statement best describes the movement of the magnet when the potential difference is 0?
Sorry, could you repeat the question?
Alright, so here we have this, basically we have this graph for the potential difference, right? Which statement best describes the movement of the magnet at these points wherein the potential difference is 0? So is it accelerating upward, constant speed upwards, decelerating downwards, or stationary? You have to tick 1 box.
Stationary.
It's stationary. Okay, correct. Any reason why?
Yep.
Do you know why though?
I was just told it was stationary.
Okay. Now the idea here is okay. The idea here is for both of these accelerating upwards and decelerating downwards. That's definitely changing magnetic field, right? Stationary, this is definitely the magnetic field isn't changing, right? Here, constant speed, this could be tricky, but remember that the fact that even though the magnet is moving at a steady speed, it's still moving, and the magnetic field itself is changing as long as the bar magnet moves. Okay. All right. Next question. Cannot detect small vibrations. Suggest 2 changes to the design that would make it more sensitive. Oh, this one's interesting. I wouldn't know. Let's see. I wouldn't know from the top of my head. I gotta think about it.
That's pretty easy. You would add more turns to the coil.
Uh-huh. Correct. That's one.
Oh, how strong the magnet is.
Exactly. Good.
Magnetic field.
Right. Because again, since you want a more sensitive, you want it to be more sensitive, you need the voltages produced to be bigger. So those are the 2 ways you can do it. Okay, great. Right, we have this.
Did you say stronger magnetic field or stronger magnet?
Stronger magnet.
Stronger magnet creates a stronger magnetic field.
Exactly. Okay. All right, so let's move here to number 4. New problem. Okay. How high would the water be in 2, 3, and 4?
How am I supposed to know?
Oh, you haven't learned this yet, huh?
Um,
Okay, I'll give you a clue.
It looks like very confusing.
Well, okay, I'll give you a clue here. Well, here's the thing.
It should be
This
all
water's
balanced.
level here, right? The water's level here, right? So
Yeah.
here it should be.
Oh yeah. Okay. Then they should all be level. If it's
They
not
should-
moving, then they should all be the same.
Yeah. Exactly. Okay. The further okay, so in this case, have you learned pressure yet?
Nope.
Ah, okay, that's why you don't know this. I guess we can skip this then for now. Okay. We can
So, I have to learn more physics.
yeah, but we can learn about this later. We can learn about this later. Don't worry. We can skip this. Okay. Oh, how about this? Reflection of light. Let's take a look at your excuse me. Let's take a look at your topics again. Waves, yeah. This is under waves. Okay. We have table 2. Here are the results. Okay. And for each angle of incidence, this was caused by... Okay, what type of error would have caused each angle of reflection to have a range of values?
Sorry, can you repeat the question?
Okay, so the idea here, here's the idea. You have this apparatus here to investigate the reflection of light by this plane mirror. Okay, 4 diagrams were drawn, and these are the results for each of those incident angles and angles of reflection. The question is this. Okay, I'll keep the data on the top of the page for now.
Okay. To be random, there's no, could be anything.
Okay.
Human error is insufficient.
Not really. Okay, I'll give you a clue. It's actually visible on the diagram here. Look at the ray box. Look at this ray of light. This is quite wide, isn't it? So what could have caused
Wait,
this?
what's wrong with it?
Again, look at the ray. Ideally, that should be a line.
Yeah.
Ideally, that should be a line. But you can see here, it's not a line. It's like a band.
Line with what exactly?
It's not a very fine line, is it? It's a very thick line. So much so that I would call